It's the most powerful technology of our time. But how does artificial intelligence actually work? We're pulling back the curtain. This is AI Deconstructed.
In our last episode, we charted the turbulent history of early artificial intelligence. We rode the wave of the Golden Age, a time of profound optimism, fueled by the belief that human cognition, logic, reasoning, and problem-solving could be captured in code and symbolic manipulation. We saw how researchers built systems that could solve algebra problems and play checkers, seemingly on the verge of a true thinking machine. Then we weathered the AI winters. We saw how this initial optimism shattered against the wall of computational reality. The problems were far more complex than anticipated. The common sense knowledge we humans take for granted was impossibly vast, and the computers of the day simply lacked the power to handle the combinatorial explosion of possibilities. The promises were too big, the funding dried up, and the field entered a period of quiet, necessary introspection. That history, that cycle of boom and bust, sets the stage perfectly for today's topic. It begs the question, what were those early researchers actually trying to do? When they claimed an AI could solve a problem, what did that look like under the hood? They weren't using the neural networks or massive datasets we have today. They were using logic, and as we'll explore today, they were using search. This is our first step into part 2 of our curriculum, the pillars of classical AI. We are moving from the history of AI to its foundational mechanics. Imagine you're standing at the entrance to a vast ancient hedge maze. The towering green walls twist and turn, branching into countless identical-looking paths. Your goal is simple. Find the exit at the center. But how do you begin? Do you cautiously explore every path near the entrance before venturing deeper? Or do you pick one path and follow it relentlessly, hoping it leads you to the goal, only backtracking when you hit a dead end? This feeling of being lost, of needing a systematic way to explore a complex space of possibilities, is not just the challenge of a physical maze. It is the fundamental challenge at the heart of a huge class of problems that artificial intelligence was first designed to solve. How do you find the shortest sequence of moves to solve a Rubik's Cube? How does your GPS navigate the labyrinth of city streets to find the fastest route from your home to a new restaurant? How does a chess AI peer into the future, exploring the branching possibilities of its next move to find one that leads to checkmate? At their core, all of these are search problems. Each one involves navigating a massive invisible maze, a maze of potential states, choices, and outcomes, in search of a path from a starting point to a solution. Today, we will formalize this idea. We're going to learn how to take a vague problem and translate it into a concrete, machine-readable problem space. We'll deconstruct how early AI was built on this elegant idea of turning any problem into a search, and we'll dissect the first, most fundamental strategies computers use to navigate these abstract mazes when they have no map and no compass to guide them: breadth-first search and depth-first search. This episode is the bedrock for so much of what follows. Understanding how a machine systematically explores a maze of possibilities is the first step to building a genuine, under-the-hood literacy in artificial intelligence. Let's begin by building our maze. To command a computer to navigate a maze, we must first provide it with a perfect map and a dictionary. We need to translate the intuitive challenge of solving a problem into a language the machine can understand. In AI, we call this a state space, or a problem space. This is the single most important concept from classical AI. It's the idea that we can represent any well-defined problem as a set of defined states and the transitions between them. A state is simply a snapshot, a single, valid configuration of the problem at a particular moment in time. Each state is a specific location, a junction or a dead end, within our abstract maze. A perfect classic example is the 8 puzzle. You've probably seen one. A 3x3 grid with 8 numbered tiles and 1 blank space. The goal is to slide the tiles around until they're in numerical order. Let's frame this as a formal search problem. What is the initial state? This is the starting point of our search. It's the specific, jumbled arrangement of the 8 tiles when the problem is presented. It is the entrance to our maze. What is the goal state? This is the destination we are trying to reach. In the 8 puzzle, it's the single desired configuration where tiles 1 through 8 are in order. More formally, we have a goal test, a simple function that looks at a state and returns either true, this is the solution, or false, keep looking. And finally, what are the operators, or actions? These are the rules that govern how we can move from one state to another. They are the legal moves. For the 8 puzzle, the operators are sliding an adjacent tile into the empty space. For example, slide the blank space up, slide the blank space down, slide the blank space left, and slide the blank space right. Of course, not all operators are legal in every state. These are the pathways connecting different locations in the maze. The transition model is the engine of the search. It's a function that takes a current state and an operator as input and returns the new state that results from applying that operator. Together, these components, the initial state, the operators, and the goal test, define the entire state space graph. The states are the nodes of the graph, and the operators are the edges connecting them. The problem is now to find a path, a sequence of operators, that leads from the initial state node to the goal state node. With these components, we can visualize the process of solving the problem as exploring a search tree. The root of the tree is the initial state. From the root, we draw a branch for each possible action we can take. Each branch leads to a new node, which represents the new state we've reached. From each of those nodes, we can branch out again and again, creating a vast, sprawling tree of possibilities. The solution to the problem is a path from the root of this tree down to a node that matches the goal state. This formalization of a problem into a state space is an incredibly powerful idea. It gives us a clear, machine-readable structure to work with. However, this clarity comes at a price. The very act of defining the state space often reveals a problem's hidden and often terrifying complexity. For the 8 puzzle, the total number of possible reachable states is 181,440. That's a large number, but a modern computer can handle it. But what about a slightly more complex problem? Let's consider the classic video game Pac-Man. To define the state space for Pac-Man, we must identify all the variables that make up a unique snapshot of the game. A simplified version might include Pac-Man's position. Let's say there are 120 possible XY locations. Pac-Man's direction. He can be facing north, south, east, or west. That's 4 possibilities. Ghost positions. If there are 2 ghosts and each can be in 12 distinct locations. The total number of ghost configurations is 12 times 12, which is 144. And finally, food pellet configurations. If there are 30 food pellets on the board, each pellet can either be eaten or not eaten. That's 2 possibilities for the first pellet, 2 for the second, and so on. The total number of food configurations is 2 to the power of 30. To find the total size of the state space, we use the fundamental counting principle and multiply these possibilities together. 120 times 4 times 144 times 2 to the power of 30. 2 to the power of 30 is over a billion. The final number is approximately 74 quadrillion states. That's 74 followed by 15 zeros. This phenomenon is known as combinatorial explosion. As you add more variables or more options to a problem, the size of the state space doesn't just grow, it explodes exponentially. This reveals a profound truth about problem solving. The act of making a problem computationally tractable by defining its state space simultaneously exposes its inherent, often unmanageable scale. It tells us that for most interesting problems, we can never hope to build the entire map of the maze ahead of time. It's simply too big, we cannot explore it randomly, and we cannot check every single state. This is not a failure of the state space model, it's a fundamental property of complexity itself, and it's precisely this challenge that makes the next step so critical. We don't need a complete map, we need intelligent strategies for exploring this impossibly vast, unseen world on the fly. We need search algorithms. So, we find ourselves at the entrance of a quadrillion path maze with no map. How do we proceed? The most basic strategies we can employ are what AI researchers call uninformed search, or sometimes more evocatively, blind search. The name says it all. These algorithms are blind because they have no additional information about the problem beyond its basic definition. They know the initial state, how to generate new states using the operators, and how to check if a state is the goal. That's it. They have no hints, no rules of thumb, no sense of whether a particular move is getting them warmer or colder in their search for the goal. Let's use a simple analogy. Imagine you're in a large, unfamiliar office building, and you need to find a specific colleague's office, room 402. You have no directory, no map, and no one to ask for directions. An uninformed search strategy would be to systematically explore the building based only on its physical layout. You could, for instance, start on the first floor and check every single room, 101, 102, 103, before moving to the second floor and repeating the process. You are operating blind, with only the rules of the environment to guide you. You have no clue that room 402 is probably on the fourth floor. These blind search algorithms are the bedrock of the field. They are simple, systematic, and in some cases guaranteed to work. The two most famous and fundamental are breadth-first search and depth-first search. Before we unleash them, we need a way to judge them. In AI, we use 4 key metrics to evaluate any search algorithm. First, completeness. Is the algorithm guaranteed to find a solution if one exists? Second, optimality. Is the algorithm guaranteed to find the best solution? In search, best usually means the shallowest solution, or the one with the lowest path cost. Third, time complexity. How long does it take to find a solution? We measure this in terms of how many nodes it has to expand. Fourth, space complexity. How much memory or RAM does the algorithm need to run? We measure this by the maximum number of nodes it has to store in memory at any one time. As we're about to see, the tension between these 4 properties, especially between optimality and space, defines the entire landscape of search. Our first algorithm, breadth-first search, or BFS, is the most cautious, meticulous, and systematic explorer imaginable. Its strategy is to explore the search space layer by layer. It's like dropping a stone in a pond and watching the ripples expand outwards. BFS first examines all the states that are just one step away from the initial state. Then, it examines all states that are 2 steps away, then 3, and so on until it finds the goal. The magic that enables this perfectly orderly, level-by-level exploration is a simple but powerful data structure, a first-in, first-out queue. We'll call it a FIFO queue. A queue works just like a line at a grocery store. The first person to get in line is the first person to be served. The set of nodes we've discovered but haven't yet explored is called the frontier. For BFS, the frontier is a queue. Let's walk through how BFS would explore a simple maze using this cue. Let's say our maze has junctions labeled with letters, and we start at A step 1. We begin at the initial state, A, we add A to our queue. The queue now contains just A step 2. We take the first item out of the queue, which is A, we explore it by finding all of its immediate neighbors. Let's say they are B and C, we add them to the back of the queue. The queue now contains B, then C step 3. We take the next item from the front of the queue, which is B. We find its neighbors, say D and E, we add them to the back of the queue. The queue is now C, then D, then E step 4. Now here's the crucial part. The next node we explore is the one at the front of the queue. C, we find its neighbor, F, and add it to the back. The queue becomes D, then E, then F. Notice the pattern. Because we always process the oldest node in the queue, the one that was added first, we are forced to explore all of A's neighbors B and C before we explore any of their neighbors D, E, and F. This first-in, first-out mechanism is what guarantees the strict, layer-by-layer progression. To prevent infinite loops, we also maintain an explored set, which is just a list of every node we've ever expanded. We only add a new child to the queue if it's not already in the explored set and not already waiting in the frontier. Now let's judge BFS on our 4 metrics. First, completeness. Is BFS guaranteed to find a solution if one exists? Yes, absolutely. Because it explores level by level, it cannot get permanently lost down an infinitely long path. Eventually, it will reach the level where the goal node resides. Second, optimality. Is BFS optimal? Yes, but with an important condition. It finds the optimal solution only if all the steps or actions have the same cost. In an unweighted graph, where every edge traversal costs 1, BFS is guaranteed to find the path with the fewest steps. This is a direct consequence of its level-by-level search. The first time it touches the goal node, it must have done so via the shortest possible path. This shortest path guarantee makes BFS incredibly useful in the real world. In social networks, when LinkedIn or Facebook tells you that you are a second-degree connection to someone, it has likely used a BFS-like algorithm to find the shortest chain of friends that connects you. A search engine crawler might use BFS to discover and index a website. Starting from the home page level 0, it finds all pages linked directly. Level 1, then all pages linked from those, level 2, and so on. But BFS has one massive drawback: memory. Let's look at time complexity. In the worst case, BFS has to explore every node. Let's say B is the branching factor, the average number of children each node has, and D is the depth of the solution. The time complexity is dominated by the last level. So we say it is big O of B to the power of D. This is an exponential time complexity, and it is terrible. But time isn't even BFS's biggest problem. Its biggest problem is space complexity. How much memory does it need? The algorithm has to store the entire frontier in memory. To explore level D, it has to store all the nodes at level D in its queue. This means the space complexity is also big O of B to the power of D. This is the Achilles heel of breadth-first search. In practice, BFS doesn't run out of time, it runs out of memory. Your computer's RAM will fill up and the program will crash long before the CPU has a chance to finish. This catastrophic space problem leads us directly to our second algorithm, one designed specifically to solve it: depth-first search, or DFS. If BFS is the cautious, systematic planner, depth-first search is its polar opposite. DFS is the aggressive, daring, go-for-broke explorer. Its strategy is to pick a single path and follow it as deep as it can possibly go. It plunges into the maze, never looking back, until it either finds the goal or hits a dead end. Only then does it backtrack to the most recent junction where it had an unexplored choice, and then plunges down that new path. The mechanism behind this relentless deep-diving behavior is, once again, a simple data structure. A last-in, first-out stack. We'll call it a LIFO stack. A stack works like a pile of plates. The last plate you put on top is the first one you take off. Let's revisit our maze explorer, this time armed with a stack instead of a queue. We start at A step 1. We begin at A. We push A onto the stack. The stack now contains just A step 2. We pop the top item from the stack, which is A. We find its neighbors, B and C. We push them onto the stack. Let's say we push C first, then B. The stack is now B on top with C below it. Step 3. We pop the top item, which is B. We find its neighbors, D and E. We push them onto the stack. Let's say we push E first, then D. The stack is now D on top, then E, then C. Step 4. Now here's the crucial difference. The next node we explore is the one on top of the stack, D. We don't go back to C. We immediately explore the child of the most recently discovered node. We will continue to follow the path starting with D all the way to its end. This last-in, first-out mechanism, always processing the newest node added, is what forces the algorithm to dive deeper and deeper down a single branch of the search tree before it ever considers exploring a sibling branch. This fundamentally different behavior gives DFS a very different set of properties. First, completeness. Is DFS complete? No, not in all cases. If the search space is infinite or contains cycles, DFS can get lost. It might follow an infinitely long path, or get stuck in a loop, endlessly exploring the same set of nodes without ever backtracking to find a solution that might be just one step away from the start on a different path. Second, optimality. Is DFS optimal? No, not at all. It explores paths based on the arbitrary order it discovers them, not based on their length. It is very likely to find a long, meandering path to the goal simply because that was the first path it explored, completely missing a much shorter path that it hasn't gotten around to checking yet. So, if it's not guaranteed to find a solution, and the solution it finds is probably not the best one, why would anyone use DFS? The answer lies in its applications and its incredible memory efficiency. The DFS strategy is a very natural way to solve problems like a physical maze or a Sudoku puzzle. It mimics how a human might work. Try one approach, and if it doesn't work out, backtrack and try another. In complex projects, some tasks must be completed before others. DFS is used to find a valid linear ordering of these tasks, a process called topological sorting, and the very flaw that makes DFS incomplete, its tendency to get stuck in loops, can be turned into a feature. It is an excellent algorithm for detecting if a network or a data structure contains a cycle. The most significant advantage of DFS, however, is its low memory usage. Unlike BFS, which might need to store an entire level of the search tree, DFS only needs to store the nodes on the single path it is currently exploring. This makes its memory requirement exponentially smaller than BFS in many cases. Let's look at its space complexity. The stack only ever contains the parent and uncle nodes of the one node it's currently expanding. How many nodes is that? It's the branching factor, B, times the maximum depth of the path, let's call it M. The space complexity is big O of B times M. This is linear space complexity, not exponential. This is the killer feature of depth-first search. It's the difference between a universe of memory and something that fits in a few kilobytes. So, let's put our two algorithms side by side. A common question that arises is, which algorithm is better, BFS or DFS? This is a classic misconception. There is no universal better. The choice is entirely context-dependent, a strategic decision based on the structure of the problem and the resources you have available. Let's do a head-to-head comparison. Traversal style, BFS explores level by level. DFS explores path by path, diving deep. Data structure. The core of BFS is the first in, first out queue. The core of DFS is the last in, first out stack. Completeness. BFS is complete. It will always find a solution if one exists. DFS is not complete for graphs with infinite paths or cycles. Optimality. BFS is optimal for unweighted graphs. It is guaranteed to find the path with the fewest steps. DFS is not optimal. Time complexity. In the worst case, both algorithms may have to explore every node, which is exponential or big O of b to the power of d. Space complexity. This is the most critical difference. The space complexity of BFS is exponential, big O of b to the power of d. The space complexity of DFS, however, is only linear in the depth of the search, big O of b times m. This exponential difference in memory usage is often the deciding factor. The reality is that in many real-world, massive problems, BFS is impossible to use. Its exponential space complexity means it will always fail by running out of memory. DFS, despite its flaws, can actually run. It can actually find a solution, even if it's not the best solution. This discussion of complexity is not just theoretical. It has profound historical consequences. The exponential time and especially space complexities of these blind search algorithms were a primary reason that the initial boundless optimism of AI's golden age came to a screeching halt. Researchers in the 1960s and early 1970s had this powerful framework of state space search. They could, in theory, solve any well-defined problem. But when they tried to apply these methods to real-world challenges like machine translation or complex robotics, they crashed headfirst into the wall of combinatorial explosion. The state spaces were too large, and their blind search algorithms were too inefficient. The computational resources required grew exponentially, far outpacing the hardware improvements of the day. This failure to scale from toy problems like the 8 puzzle to meaningful, real-world applications led to widespread disillusionment. Grand promises went unfulfilled. In the mid-1970s, government agencies and influential reports heavily criticized the lack of progress and cut funding for AI research across the board. This period, from roughly 1974 to 1980, became known as the first AI winter. It was a time of reduced funding, waning interest, and a general sense that AI had been overhyped. This winter was not just a failure of funding or imagination. It was a direct, predictable consequence of a fundamental collision. On one side, you had the exponential complexity inherent in interesting problems. On the other, you had search algorithms whose resource requirements were also exponential. When you apply an exponential algorithm to an exponential problem, the result is a computational firestorm that no machine can handle. The AI winter was in many ways an inevitable outcome of the theoretical limitations of the blind tools available at the time. To emerge from this winter, AI needed more than just faster computers. It needed to learn how to see. The fundamental problem with breadth-first and depth-first search is their blindness. They explore the maze with no sense of direction. Systematically, but unintelligently. How could we make them smarter? What if, at every junction in the maze, we had a magical signpost that pointed in the general direction of the exit? We might still take some wrong turns, but we would be far more efficient than just trying every path. This magical signpost is the core idea behind informed search, and the mechanism for creating it is called a heuristic. A heuristic is an educated guess, a rule of thumb, or a problem-specific approximation that estimates how close a given state is to the goal. It's a piece of extra knowledge, beyond the basic problem definition, that can guide the search more intelligently. Let's return to our analogy of finding room 402 in an unfamiliar building. The uninformed searcher, BFS, checks every room on the first floor, then the second, then the third. The informed searcher uses a heuristic. The heuristic is the simple rule of thumb. The first digit of a room number usually corresponds to the floor number. Armed with this knowledge, the informed searcher doesn't waste time on the first 3 floors. It goes directly to the 4th floor and begins its search there. It has used a clever guess to dramatically prune the search space. This is the power of a good heuristic. It allows an algorithm to prioritize more promising paths, saving an enormous amount of time and computational effort. The quintessential, most famous, and most widely used informed search algorithm is called a search, or as it's more commonly known, a star. A star is a brilliant synthesis that combines the best aspects of the algorithms we've discussed. It seeks to merge the systematic path-cost tracking nature of algorithms like BFS with the goal-directed guidance provided by a heuristic. At the heart of a star is its famous evaluation function, which it uses to decide which path to explore next, for any given node or state, which we'll call an. The function is f of n equals g of n plus h of n. Let's break this down intuitively. G of n is the known cost. This is the actual measured cost of the path from the starting node all the way to the current node n. It represents the past, what we know for sure. This is the part that a systematic algorithm like BFS cares about. H of n is the heuristic cost. This is our educated guess, the estimated cost of the cheapest path from the current node n to the goal. It represents the future, our best guess about what's to come. This is the part that gives the search its sense of direction. F of n is the total estimated cost. A star works by always choosing to explore the node with the lowest f of n value. It constantly balances the cost of the path it has already traveled with its estimate of the cost remaining, ensuring it focuses on paths that are not only heading in the right direction but are also efficient overall. For a star to be not just fast, but also optimal, that is, guaranteed to find the best solution, its heuristic must have a special property. It must be admissible. An admissible heuristic is one that is optimistic. It never overestimates the true cost to reach the goal. A classic example is finding a driving route between 2 cities. The straight line as the crow flies distance between the 2 cities is an admissible heuristic. Why? Because the actual road distance can never be shorter than the straight line. It might be much longer due to winding roads, but it can't be shorter. Using an admissible heuristic like this ensures that a star doesn't get so focused on a seemingly direct path that it misses a slightly longer, but ultimately much faster route via a highway. Today, we have journeyed deep into the foundations of AI problem solving. We learned how to frame almost any problem as a search through a state space. We explored our 2 fundamental blind strategies: breadth-first search, the cautious explorer, guaranteeing the shortest solution but at a massive memory cost, and depth-first search, the daring explorer, saving memory but sacrificing completeness and optimality. We saw this as a critical trade-off. We then connected these limitations to history, understanding how this collision with exponential complexity contributed to the first AI winter. Finally, we saw a glimmer of light, a path out of the winter, the introduction of the heuristic. In our next episode, we will fully embrace this new paradigm. We will leave the world of blind explorers behind and delve into the mechanics and power of informed search, putting the A*STAR algorithm and its brilliant use of heuristics under the microscope.
You've been listening to AI Deconstructed. Join us next time as we unpack another layer of the technology shaping our future. Until then, stay curious. Subscribe for more.